Imagine you want a neural network to dream up brand new photorealistic images of faces, or generate audio that sounds like human speech or sketch novel handwritten digits. The challenge is fundamentally different from classification. When you train a classifier, you have clear labels and a clean gradient signal telling the model when it is wrong. But when you ask a network to generate something new, what does wrong even mean? How do you define a loss function for creativity? For years, the dominant approach to this problem was to explicitly model the probability distribution of the data. Researchers built things like restricted Boltzmann machines and deep belief networks, which try to write down a mathematical formula for how likely any given image is under the model. The trouble is that these formulas almost always contain an intractable normalization term, a sum or integral over every possible configuration of the data, which is astronomically expensive to compute. So practitioners had to lean on Markov chain Monte Carlo methods, slowly walking through the space of possibilities to approximate gradients. These chains are slow, they get stuck, and they fight against the very techniques like piecewise linear activations and dropout that make discriminative deep learning work so well. Other approaches like denoising autoencoders and generative stochastic networks tried to learn one step of a Markov chain at a time, but they still inherited the mixing problems of chain-based sampling. The paper we are looking at proposes something startlingly different. Instead of trying to write down a probability density at all, you train two neural networks against each other in a game. One network, the generator, takes random noise as input and tries to produce samples that look like real data. The other network, the discriminator, looks at a sample and tries to decide whether it came from the real dataset or from the generator. The famous analogy the authors use is counterfeiters versus police. The counterfeiters keep refining their fake bills. The police keep refining their detection methods, and in equilibrium, the counterfeits become indistinguishable from real currency. Crucially, no one ever has to write down what makes a bill look real. The discriminator learns that implicitly, and its judgment becomes the loss function for the generator. Now let's get into how this actually works. You define a prior distribution over noise vectors, typically something simple like uniform or Gaussian. The generator is a multilayer perceptron that maps a noise vector to a data sample, say an image. The discriminator is another multilayer perceptron that takes an image and outputs a single number, the probability that the image is real. The training objective is a two-player minimax game. The discriminator tries to maximize the expected log probability it assigns to real data plus the expected log probability of 1 minus its assessment of fake data. The generator tries to minimize that same quantity, specifically the part where the discriminator catches its fakes. In plain terms, the discriminator wants to score reals high and fakes low, and the generator wants to fool the discriminator into scoring its fakes high. In practice, you alternate. You take a few gradient steps on the discriminator with a mini batch of real samples and a mini batch of generated samples. Then you take a gradient step on the generator. There is a subtle but important trick here. Early in training, the generator produces obvious garbage, and the discriminator easily rejects it with very high confidence. When that happens, the original generator objective, which is to minimize the log of 1 minus the discriminator's score on fakes, saturates and produces tiny gradients. So instead, the authors flip it around and train the generator to maximize the log of the discriminator's score on its fakes. Same fixed point, much healthier gradients early on. It is a small change with a big practical effect. The theoretical analysis is elegant. If you imagine the networks have unlimited capacity, you can ask, for any fixed generator, what is the optimal discriminator? The answer is that the discriminator should output the ratio of the real data density at a point to the sum of the real and generated densities at that point. Plug that optimal discriminator back into the game, and the generator's objective simplifies beautifully into a constant minus twice the Jensen-Shannon divergence between the real data distribution and the generated distribution. Jensen-Shannon divergence is a symmetric measure of how different two distributions are, and it is zero only when they are identical. So the unique global optimum of this game is the generator perfectly matching the data distribution, at which point the discriminator is left guessing with probability 1/2 everywhere. That is a clean and satisfying result. The experimental results in this paper are modest by modern standards. The authors train on MNIST handwritten digits, the Toronto Face database, and CIFAR 10. Because there is no explicit density, evaluating the model is awkward, so they fit a Parson window around the generated samples and report log likelihoods. On MNIST, they report about 225 nats. On the Face database, about 2057, which are competitive with deep belief networks and stacked contractive autoencoders. They also show that interpolating linearly in the noise space produces smooth transitions between generated digits, suggesting the generator has learned a meaningful manifold rather than memorizing training examples. Now the limitations, and the authors are admirably candid about them. There is no explicit representation of the learned probability density, so you cannot directly compute how likely a given image is. The training dynamics are delicate. The generator and discriminator must be kept roughly in balance, because if the discriminator gets too good too fast, the generator's gradients vanish, and if the generator races ahead, it can collapse, mapping many different noise vectors to the same output and losing diversity. The authors call this the Helvetica scenario, what later became known as mode collapse. And while the theoretical convergence proof is clean in the non-parametric limit, once you parameterize the generator and discriminator as actual neural networks with finite capacity, the loss surface has many critical points and none of the convergence guarantees strictly apply. Looking forward, the authors sketch a number of extensions that turned out to be remarkably prescient. Conditional generation by feeding labels to both networks. Learned inference networks that map data back to the latent space, and using the discriminator's features for semi-supervised learning. Each of these became a major research direction in the years that followed. This paper is essentially the seed of an entire ecosystem. Now let's walk through some questions you might have after hearing all of this. First, why does pitting two networks against each other work better than just training one network to maximize likelihood directly? The key insight is that the discriminator provides a learned, adaptive loss function for the generator. Instead of you specifying ahead of time what makes a good image, like pixel-wise mean squared error, which leads to blurry results, the discriminator discovers the relevant features automatically and keeps raising the bar as the generator improves. It is a curriculum that creates itself. Second, what exactly goes wrong in mode collapse, and why is it such a persistent problem? If the generator finds even one output that consistently fools the current discriminator, it has every incentive to keep producing that same output, regardless of the input noise. There is no term in the loss that explicitly rewards diversity, only fooling the discriminator. The discriminator eventually catches on and learns to reject that particular output, but by then, the generator may have lost its grip on other modes of the data. The game can oscillate rather than converge, especially because the two networks are chasing a moving target in each other. Third, why can't you just train the discriminator to convergence at each step, given that the theory assumes an optimal discriminator? Two reasons. Computationally, it is wildly expensive, and statistically, on a finite dataset, a fully optimized discriminator will overfit and become perfect at distinguishing the specific real samples from any fake, which provides essentially no useful gradient to the generator. So in practice, you keep the discriminator close to optimal, but not all the way there, taking a few steps at a time and relying on the assumption that as long as the generator changes slowly, the discriminator stays in a useful neighborhood. So how could these ideas apply to large-scale recommendation systems serving hundreds of millions of users? One concrete angle is candidate generation. Adversarial training can help build generative models of user behavior, like sequences of items a user might plausibly engage with, where a discriminator tries to distinguish real engagement sequences from synthesized ones. This gives you a principled way to augment sparse interaction data, simulate counterfactual user trajectories for off-policy evaluation, or generate diverse candidates that match the distribution of authentic user interest rather than collapsing onto the popular head. The adaptive loss idea is especially powerful here because handcrafted objectives for sequence realism are notoriously hard to specify. Another practical application is in ranking and exploration. The discriminator framework naturally yields a model that estimates the ratio of two distributions, which is exactly what you want for things like importance weighting in counterfactual learning, detecting distribution shift between training data and live traffic, or flagging low-quality synthetic or bot-generated content in your training pipeline. And the mode collapse failure mode is itself a useful warning. Anytime you train a generative model of user interest, you have to actively guard against the system converging on a narrow slice of safe, popular recommendations, which is the same diversity problem recommender teams already wrestle with daily.